Hey class, be sure to check e-learning. I've posted the exam review, um, so give it a shot. We'll review it here now. So if you don't want to give it a shot, if you just want to go through it with me, yeah, that's all right too. I will post the solutions sometime before the exam itself is due. I'm not going to put an actual date on that just yet. Um, and then we'll spend the first part of the class going over the review, and then the second part of the class going over the final section of the lecture notes, which is a precursor to the section of the class that's over proofs, the part where we start proving stuff. And so, just like the coding part of the class, we spend a fair amount of time coding. The proving part of the class, we're going to spend a fair amount of time proving. I am already questioning myself how I'm going to handle this third exam. I'm not quite sure, but it may be proof heavy. And if so, then I highly encourage you to ace this one. It won't be that bad. Yeah, let's jump into it. You should be fine. But definitely embrace for this exam, embrace the coding, and for the next one, make sure you are diligent in doing the homeworks, and that'll really help you. Okay, let's see. Okay, so there's only two main problems for this exam. There's the one on graphs and the one on trees, and then there's some sub problems. Okay, so for the one on graphs, use Dijkstra's algorithm to identify the shortest path between nodes D and E with respect to the following graph. Okay, so we start here and we get here. And if you remember Dijkstra's algorithm, it should remind you a little of Prim's algorithm in that there's this creeping structure where we extend out from whatever our start node is, and then we make sure that we've considered essentially every possible edge, and in doing so we end up constructing the shortest path from whatever our source node is to essentially every other node in the graph. And we do so in a reasonable runtime, actually. And so, it can be done by hand, but let's discuss Dijkstra's on the chance that I end up giving you a graph that is more difficult than this one, and you end up needing just a little bit more. So, okay. So we have some start node, some source node, and then we consider its adjacent vertices. Okay, so we have C and H. So if you recall our breadth search, or our breadth first approach, we take the neighboring vertices of D, and then we consume each of the edges, and we say, okay, well, we have a shortest path from D to C, and then a shortest path from D to H. Okay, so our current shortest path for D to C has length 1, and so because this is the first adjacent node that we've considered, we then take the edges from this one, excluding any nodes that have already been solved. Okay, and so from D to C we have B, G, or B and G, and then we exclude D because D has already been solved. And so then we go from C to G, and we say, okay, well, we update our shortest paths, and we say, okay, well, we have a new shortest path for G, and we have a new shortest path to B, and then we pull from this, and we say, okay, well, Next, we test out H, which was the next one in line for D, and we say, okay, well, we consume the edges from H that are incident to H, and we have one running back to D. Well, we ignore that because D is already solved, and then we go to G, and we say, okay, well, we have a new shortest path from, and so then we go to G, and we see whether or not the path from DHG is shorter than whatever the shortest path to G is. Say, okay, the current best approach to getting there is only a weight of 3, and our new approach is a weight of 8, so that's not it. And so we have exhausted those edges, and then that's it. So H is now considered to be solved, and so the next node up would be B, and then G, and then A, and then F, and then E. And so along the way, you have to maintain and update these shortest paths, and then always considering what has actually been solved, and then iteratively increasing it. Now, what I'm going to encourage you to do is refer to the code that's already been provided to you. So you were given an implementation of Dijkstra's algorithm. So make sure that you understand it. Ideally you would have written your own version of it, and then if nothing else, then you can use it to verify your answer. But I can guarantee that the question on the exam will not necessarily duplicate what was provided to you. So just make sure that you understand what's going on with Dijkstra, and if you have any questions, feel free to reach out to me and we can discuss it again. Okay, or rewatch the lecture where we covered Dijkstra. Okay. So Prim's the next one is going to be over Prim's algorithm to find a minimum spanning tree, and so again, it's one that the conception is pretty easy. You're trying to find a tree structure in this which has a minimum sum total of weights, and so we just went over that. And again, you have code that you can refer to, and again, it will not be entirely necessarily straightforward in terms of applying that code to whatever's on the exam, but you should do all right if you've been following along. And then again, you can always rewatch the lecture if you have if you need a refined understanding of it. Okay, and then the third one, Kruskal's algorithm, and I will supply the graph again, you're finding a minimum spanning tree, but I will supply the graph in an alternative definition. You will get one where you're given an adjacency matrix, and that'll be how the graph is defined, and then you'll be expected to provide the minimum spanning tree from that. Okay, trees. So on this one, you'll be given a tree and a callback function. It'll be written in JavaScript syntax, and then you'll be expected to say what the output is given a certain method of graph or tree traversal. In this case, it's post-order traversal. Okay, and then in this one, for this problem, I've asked you to use a breadth-first traversal to generate a tree. So it's not necessarily a minimum spanning tree, but it's unweighted. So we're visiting the nodes in the graph in a unique order. And so this is perhaps the easiest version of generating a tree from a graph, in that you have to make sure that you visit each node only once. And so that's pretty simple. Right, so you start here, and then you queue each of the children each of the adjacent nodes in lexicographic or alphabetic order in this case. So it would be B, C, D, and E, and then those define which ones you're visiting next, and so forth. Again, I'll post the solutions before the exam actually happens, and then you'll be given a coding problem. And so for the review, I've asked that you write a JavaScript function that retrieves the HTML body element from an HTML document, and then performs a breadth first traversal and invokes a callback, a supplied callback whenever an image tag is encountered. And so we'll go ahead and do this one, and then we'll jump into the lecture notes. Okay. Alright, so the first thing that we need to do is make sure that we can access the body element. HTML documents, like the even higher level than the HTML tag, is the document definition itself. And so you'll see that the entire document is provided in that. So the body element is directly accessible just through document.body. So I've asked that we write a function that retrieves the body element. So we already know how to get the body element. It's just document.body. And then performs a breadth first traversal of the body's subtree. So let's write a function that performs a traversal. So it accepts some HTML element. It has a callback, and then let's see. So there's a callback that is supplied, and in fact, let me just spell it out. Callback function, sure. And then whenever we encounter an image tag, we pass that element into the callback. So before we do this, let's just write some callback so we have some idea what it looks like. So it'll accept an HTML image element, and then it'll just alert us that it found it. For now, it really doesn't matter. The only thing that we care about is the function signature, and that it expects to receive an HTML image element. Although in JavaScript, it is super flexible, so you don't even have to worry about it compiling. But we'd say found an image element, and then we would just write that to the console. Okay, so we have a callback that we can use to test. Our traversal function would accept an HTML element, not necessarily an image element for this one. And then we want to halt. Our halting condition is that after the third image tag is discovered, we stop looking. Okay. So then we start with the body element. And we look at all of the children. Well, sorry. No, we're doing a breadth first traversal, so what we need is a Q. And we initialize it with body. And then we have some next element, which we initialize to null. And then we loop. So while next element, which is equal to Q dot shift and that'll be null or undefined whenever it's empty, and so it'll automatically terminate that way. And then also we need a way outside of the loop that we can track the number of matches. So images found, we start with 0. So either we've exhausted all of the elements in the tree, or we found 3 images. So if our number of images found is greater than or equal to 3, then we're going to break and we'll leave the function. Although we're not counting by more than 1 at a time, so we can use exactly equal to 3. Okay, and so we need to loop through all of the children elements of the current node, and then so we queue those up, and and then after the loop we check to see whether or not our current element is an image element, and if so we pass it to the callback, and then that's it. So I less than next element children I plus plus and then we just queue them up. So queue dot push, and again in a standard queue interface this would be in queue or something similar, but the way Java defines or JavaScript defines it, it's push. Okay, and so then we access it in an array fashion, and that's it. We just push all the children or enqueue them all to the end of the queue, and then we check to see whether or not our current element has a tag name of image, and if so, then we pass it to our callback function. And that's it. That's not quite it. So one of our halting criteria was that once we'd found 3 images, we would stop. In those cases, when we find one, we have to increment the counter for the number of images found. Okay. So already I can see that there's room for improvement here. The way we defined it, we didn't actually need to accept an HTML element because we were using a breadth first search. We didn't need the recursive nature of that, and in fact we explicitly grabbed the body element. So we could have left it as it was, and searched just a subtree, but we were able to pass it. And so you can see, even as I'm contriving these examples that there are multiple ways to solve these problems, and your code will evolve even whenever you have a very clear conception in your mind of how to use it. Okay, so I'll call this function, and I'll pass it the callback that we've defined, but I don't think it's actually going to identify any. Yeah, because there are no images in the document that we're looking at. But you can play around with that same code on some other site and see whether or not your instructor knows what he's talking about. Okay, so that's it. It was a really simple coding example. If you've been paying attention to the lectures, then you have some idea of what to anticipate for the exam. And if not, well, then it should be a fun surprise for you. Okay, so leading into the third part of the semester, I wanted to cover just some approaches for proofs. So either in this class or in general, you may find yourself having to prove something or wanting to prove something. And so this is kind of how I view it, and kind of the insights that I've gained into it. So it's something that is typically kind of difficult to wrap your head around at first. So solving problems with these really well-defined rules, is something that I think most programmers, developers, and engineers kind of have a knack for. So if you lay out the framework, then eventually they can finagle their way to a solution. But identifying whether or not some concept is true can be really difficult. In particular, because it's not guaranteed that such a proof even has the tools necessary to prove the assertion, one way or another. And so sometimes you're kind of waiting on math to catch up and build enough of a framework for you to approach a particular problem. And sometimes it's just that the question's a little too open-ended or poorly defined, and there's not, you have to add your own structure to get it to something where you can actually make the type of assertion one way or another that can be proved. And sometimes it's just that it's unfamiliar, that the problem is asked in a way that is deceptively difficult, which we'll cover at the very beginning. And so whenever so I studied math in graduate school, and I had a time. It was pretty difficult, and so one of the most difficult problems I faced right up front, it wasn't even given to me as part of a homework assignment. I was going to the office hours of one of my instructors. I'm pretty sure it was every day that semester, or very close to it. And he had written this book on analysis, and it started from a very, very basic build-up of the study of real analysis, and like one of the first few problems, within the first couple pages, was this one: prove that 1 is not equal to 0. And I had seen the field axioms before, but I guess I just took for granted that 1 was not equal to 0. And so I couldn't get anywhere on it, and I ended up just reading the solution, because I couldn't quite wrap my head around the idea that there was a way to prove such what I thought was a fundamental statement. And so, we'll go over the proof here in a second, but these axioms, they spent quite a bit of time paring down the list of mathematical truths to just what was absolutely necessary to actually state everything that we're taught in grade school. As far as multiplication and arithmetic and the way the actions of polynomials and everything else, and it all starts from these 9 fundamental statements, these axioms, these self-evident truths, and it's kind of amazing that they were able to get it down. But if you ever study abstract algebra, then you'll see that there are other, there are things other than the real numbers where these, if you have a set which you can make these same statements about, then you get a lot of the theorems of the real numbers for free, because really we're proving them against these statements, and if you can make those assertions, then you get them in that new field, and so the complex numbers are going to follow these same things, and then you can get these other types of algebraic structures like rings and modules by dropping some of these. Like commutativity. So most of these you can keep whenever you're dealing with matrices from linear algebra. If you deal with the group of invertible matrices, it's called the group of general linear transforms of certain rank. And so you get in that group, you get invertibility, you get an identity, you can have associativity, you get all of the additive ones. You can keep commutativity and identity and an additive inverse and associativity and even distributivity, but you lose commutativity. And so that entire field of study of abstract algebra is basically given some set of these fundamental truths, what is the most that I can say about any algebraic structure that follows those properties, so that I can prove this other thing that I need for this particular entity that I'm dealing with. And so it's different, and I found it to be extremely difficult. But if you put in the time and you put in the work, then you get a new way of seeing certain problems, and that can pay off down the line. I think it's always to your advantage to know just a little bit more and have just a little bit more understanding. So if you want something that'll stretch you, then that field will definitely do it. Okay, so as promised, let's show that the multiplicative identity 1 is not equal to the additive identity 0. Right? So we've asserted that that a field, by definition, a field will have both an additive identity and a multiplicative identity. So something that you can add that thing to, we'll call it 0, and get back whatever the other thing was that you added it to. And then something that you can multiply by, we'll call it 1, and then get back whatever you multiplied that thing by. So show that the multiplicative identity is not equal to the additive identity. So we do this first by assuming that they are the same, that we have this wondrous omni identity that's both the additive and the multiplicative identity. Then you can pick any number in the fields that we're studying, such that it's not equal to 0. Then we get the multiplicative identity of it, and then we will multiply 0 times whatever non-zero element that we've chosen from our field. And we've assumed, so by hypothesis, we've assumed them to be the same, and we'll see that this leads to a contradiction. So we make that algebraic substitution because we're assuming them to be the same. And while it's an additive identity, so we can add 0 to it and still get back the same number, right? So 0 plus 0 is the same as 0. And so we stick those in parentheses, and we have that now this is equal to this, and so this, which is equal to this, is now multiplied by our choice of A. And then by distributivity, so now we multiply A by both of our zeros. Okay. And then by our flawed assumption, we're assuming that 1 is equal to 0, so we can make that algebraic substitution in this step and get back this. So 1 times A plus 1 times A is equal to our original A. And then, because it's the multiplicative identity, this is the same as A, and this is the same as A. So now we have that A is equal to A plus A if we allow this to be true. Okay, well, we know from this one that there exists an additive inverse for any element A in our field. So we add that to both sides, and now we have on the left-hand side that is equal to 0, and on the right-hand side we associate these two and we get that that's equal to 0, and so then we get that 0 is equal to A. Well, we chose A such that it wasn't equal to 0, so that's our contradiction. So we made our choices, and our assumption that our multiplicative and additive identities were the same led to a contradiction. So it's not possible that they are the same. And so, yeah, that proof was beyond me. It's not impossible to follow. Hopefully, I was able to demonstrate it. It's not even terribly long, but it's an entirely new way of thinking, and it's from these first principles, and it can be extremely difficult at first to kind of understand what's going on. Well, I was taught that anything times 0 is 0, and anything times 1 is whatever it was, and so if you pick something that's not 0, then this is not going to lead to some contradiction where the element that we chose was again equal to 0. And so you find that you have these circular thoughts, and there's not this habituated structure of proving things from first principles, and so it's a new way of thinking. But again, it's not something that can't be overcome. It's just different, and it takes a little while to adapt. So proofs can be a strange beast at first, but just hang in there and review it again and again, and it should make sense. And you won't be able to reconstruct everything from memory or whatever at first, or create your own proofs at first, but the more time you put into it, the better off you'll be at performing that type of work or recalling the steps necessary to make a proof. Okay, so here's another tricky one. So we've shown that 1 is not equal to 0. Let's prove that 1 is greater than 0. This one's even nastier because you actually have to prove these 3 intermediate assertions. You have to prove that whenever you have 2 numbers that are greater than 0 and you multiply them together, you get something that is again greater than 0. So 2 times 3 is greater than, or individually greater than 0, and so their product must be greater than 0. You have to prove that. It's not one of the axioms. You have to show that if you pick a number in our field, that the additive inverse of our multiplicative identity, when multiplied to whatever number you've picked is going to give you the additive inverse of whatever value you are looking at. So basically, if you have some number like 10 and you multiply by -1, you get -10. And the relationship between a and -a is such that if you add them together, you get 0, right? So that you have this concept of the negation of your multiplicative identity interacts in that way with the way you add numbers together. So -1, while it wasn't listed in our axioms, it plays kind of a special role in constructing these additive inverses. And then you have this third assertion that if you have some number less than 0, so some negative number, then the additive inverse of it, or if you multiply it by -1, then you get something that's greater than 0. So that you're flipping it about the origin whenever you multiply it by -1. And vice versa. If you have something that's greater than 0, then whenever you multiply it by -1, you get something that's less than 0. That's not part of the axioms. It's just something that we're taught to memorize, and then proving it, again, can be extremely difficult. But I'm going to spare you that. We're not going to do it right now. I'm just going to state that it is something that actually can be proven from the axioms, and then in some cases intermediate postulates. Okay. So for now, we'll just say that they're true without proving it. Okay. So then we can use them because we're asserting that they're true. So let's again make an erroneous assumption. We'll say that 1 is less than 0, so the opposite of what we're trying to prove. Then we have that 1, our multiplicative identity, is equal to 1 times 1. Because it's multiplicative identity, we can always multiply it by 1 and get the same number back. And then we're going to say that, well, using this, that if this is greater than 0, if -1 is greater than 0, then we can multiply by -1 and get 1, which is assumed to be less than 0 right here. So we're doing this as a clever way of multiplying by 1, and so we're assuming that these are greater than 0 and this is less than 0, which again will probably blow your mind for a little bit, but again, we're assuming something that we're going to use to lead to a contradiction. So it's okay that we've assumed something false, because it is going to show that if that's the case, then it leads to gibberish, it leads to garbage, so it must be the opposite. In particular, since we've already shown that it's not equal to 0, if it's not less than 0, then by trichotomy laws, it must be greater than 0. Okay, so now we commute, and we have this 1 times this -1, and this 1 times this -1, and we end up with this. Okay, well, from this, right, we have that this is -1 and this is -1, so we get this. And then the negation of this is greater than 0 because we have the -1, so if this is less than 0, then -1 is greater than 0. So then this is greater than 0, and this is greater than 0. Well, if we have two numbers that are greater than 0 and we multiply them by each other, then we get something that is again greater than 0. So then this is greater than 0. We assumed to start that 1 was less than 0. So even when we assume that, we still can't get that in our result. So we have a contradiction. And so it's not possible for this to coincide with these, which we will say that we have previously proven. Okay, so we've done it. We've shown that 1 has to be greater than 0. Okay, so yeah, we're gonna have trouble reproducing that just off the top of our heads. So how do we do it? Like, how do we get from wherever we're starting to somewhere where we can construct either elaborate proofs or even proofs of simple concepts that we've been taught since grade school? It starts by building a repository of tricks. You just have to, study things that have been proven before and kind of keep this. It doesn't have to be an exhaustive catalog, but it's nice to have a, a bird's eye view of what has been done before. And so, a few of the things that you'll see. One is proof by contradiction. So we've already seen it twice in the last page. so, uh, so yeah, you assume something that's opposite of what you're trying to prove, and then you follow the set of logical conclusions, and then we'll see if it leads to a contradiction or something that's obviously false. Such as whenever we proved that one was not equal to zero. You start with 1 equals 0, and then it leads to a contradiction in it. That contradiction, if constructed correctly, proves what you actually wanted to prove. And sometimes if you assume something opposite to what it is that you want to prove, and it's unknown, it may be that your assumption, your original assertion was incorrect, and following the series of logical conclusions actually leads to show that you were wrong in your hypothesis, and so the proof by contradiction, or the attempt at it, actually led you in the correct direction. So proof by contradiction, it has the surface value of actually proving what it was that you were trying, and sometimes the hidden value of showing that you were wrong in your original assumption. Okay. So another trick that you'll commonly see is multiplication by 1. So you multiply both the left and the right hand side by the same thing, or you multiply by a fraction that's not 0 divided by 0. Something like a divided by a. So that's a version of multiplying by 1, but sometimes it'll allow you to get moving. So like whenever you move fractions into a common denominator, you're multiplying the numerator and the denominator by some term that makes every fraction have the same denominator, and so that's a version of multiplying by 1. And then this is another one that you'll see whenever you study differential equations. So we have this first order linear differential equation, and it is the derivative of y with respect to x plus some non-homogeneous term, p of x times y of x equals q of x, and we're trying to solve for y of x. So how do we get there? One clever way of doing it is constructing this v of x, which is equal to the integral of p of x, or specifically, using the fundamental theorem of calculus, the derivative of this is equal to p of x dx. So the derivative, if you take the derivative of both sides, then you cancel out the integral over here, you get a derivative over here, and you get p of x over here, which was over here, right? So then, yeah, like that. So then, if you take advantage of the exponential function, then you can create this integrating factor where you multiply, or where essentially you guess at a derivative that leads to a constructive result. So we were trying to solve for y of x before, and we couldn't quite do it, but this, it turns out that if you use this integrating factor and you multiply it by y of x, then when you take the derivative of that product, then you get this, right? Because the derivative of the exponential is the exponential times the derivative of whatever was inside. So here, that would be this times this. And then from the product rule, you would take the derivative. You would multiply this times the derivative of y of x, right? So that's why you get this. Well, this part, right, this part of the right-hand side was actually q of x to begin with. It's this, right? So we should recognize this. So by this clever use of the integrating factor, we were able to correctly guess a helpful antiderivative. We were able to correctly guess something that would yield a term, a multiplicative factor that looks like what we want. Well, we were trying to isolate y of x, and so now we have something on the left-hand side that if we take the integral of, this, it cancels this differential, and we have this on the left-hand side, and then we have the integral of this on the right-hand side. And so, so if we do that, then we have e to the v of x, yx over here, times the integral of this. Well, we wanted to isolate y of x, and now we just move the e to the vx, over here, and we do that by multiplying by 1, right? So we do it again. So now we multiply by both sides by e to the minus v of x, and so it cancels over here, and we get y of x isolated as desired. And then we get the inverse of that exponential over here, or 1 over e to the v of x over here, times that integral. And so we were able to isolate y of x, by a clever application of multiplying by 1. And so I love the integrating factor. I think it's a super clever solution to what I would have assumed to be an impossible differential. Anyway, okay. So then, another trick. So we can multiply by 1, and it doesn't change anything. But it sometimes, if we're clever about it, it gets us moving. We can also add 0 without changing anything, and if we're clever, it gets us moving. So think about the quadratic formula. So we have something of the form ax squared plus bx plus c equals 0. So then we switch it to a monic because we're trying to solve for x. Right? So the first thing we do is get rid of this useless a over here that's doing nothing but causing trouble. And so we divide it out, and we get it in this form. And then the real clever trick here is adding 0, but 0 that looks like this. That's b squared over 4a squared minus b squared over 4a squared. Well, this is 0. We can add that in anytime we want. And so now we use associativity, and we group this one with this. And we move that to the right side, and now we have this is equal to b squared over 4a squared minus c over a. And then we did that because we wanted to complete the square. So we have something over here, and we should be familiar at this point with x plus y squared, right? And so we want something, some x plus y that we can square. And so we have these two, and we can construct what this third term would look like just from that. And so that was why we chose this, because, well, I wanted this, and in order to get that, I have to have something that cancels it out, and then, I just balance the equation. So now I have something that's squared on the left-hand side, and then something that doesn't involve x on the right-hand side, which is brilliant, because now I can solve for x. So we just take the square root of this, right? But before we do that, we get a common denominator, right? So another clever application of multiplying by 1, 4a over 4a. We have a common denominator, so now we can stick them all under the same square root, so plus or minus the square root of this, and common denominator, so we move them all under 1. Well, this is actually this squared, so we can pull it out of the square root, and it has a common term. And this is already in the numerator. We have this, which remains in the numerator. Voila, you have the quadratic formula. So you have to keep your eye out for it. And so, it's not always obvious that sometimes these things just sit there for a while until someone with time and will comes along and just insists that they're going to find a solution. Okay, so another problem that we could consider, or another approach to some problems, is counting. And we one of the subjects within this course is advanced counting. But you can demonstrate certain properties just by creating a one-to-one correspondence. So by just showing that for every thing in set A, there is some counterpart in set B, and they have this one-to-one relationship, so that anytime you choose something from set A, there's exactly one element that matches it in set B. And for every element in set B, there is some associated element A, and that's the one-to-one correspondent. And so the way that you show that infinite sets have the same sized infinity is by creating that one-to-one correspondence. So even though it doesn't seem like it, if you consider the rational numbers, and so you have, think about every positive integer. So if you divide 1 by all of those positive integers, the infinite set of positive integers, then you get some number that's between 0 and 1. Well, we've already represented all of the natural numbers, and we've only used the set 0 to 1. So it would seem to me that if you take all of the fractions, positive and negative, and the fractions between 1 and 2 and between 2 and 3, that you must have a set that's larger. But that's not a proof. That's not a mathematical proof. It turns out that the set of natural numbers, so all of the positive integers, and the set of integers, so all of the positive and negative numbers, as well as 0, and the set of rational numbers, so all of the fractions, positive and negative, and all of them, they all have they're all the same sized set. And that's one of the things that you run into when you start dealing with infinity, is you have to define these rules that you'll operate by. And so whenever you're dealing with infinity, the one-to-one correspondence is actually what matters. And so because we can count these sets, we can line them up and just iterate over them. We could write a for loop that goes from 0 to infinity and spit out every one of these numbers through a clever ordering of them. In that regard, because we'll never exhaust the natural numbers, and because we won't miss any of the positive or negative integers or positive or negative rational numbers, we'll hit all of them too in exhausting the natural numbers. They have this one-to-one correspondence that for any one that we picked in either of those other sets, there is a natural number that corresponds to it using this clever ordering. And so therefore they have the same sized set, the same cardinality. It is the smallest of the infinities. It's called a countable infinity, because you can spit it out in a for loop. You can count your way to it, and this is a hypothetical for loop. There's not a number of bytes large enough to count to infinity, but hypothetically, right? And so, but algorithmically, you've constructed this one-to-one correspondence, and so you've shown that those infinities are all the same size. And so, the question of whether or not there's a larger infinity is answered by this failure to count. So there is a proof where you show that you can't count all of the elements of one set using this clever ordering. And so there's a diagonalization argument that's used to show that the cardinality, or the size of infinity of the real numbers, so numbers like pi and e and so forth, the ones that are that include all of the rational numbers as well as all the ones with infinite series that converge to some number. And so if you were to attempt some such ordering, so you pick however you want to sort them, however you want to order them. and then you stick them all in a column vector, essentially. And then you say, okay, well, from this first number in the column vector, or the 0th number if you're indexing properly, I'm going to take the leftmost number. And so even if you just did the numbers between 0 and 1, the real numbers between 0 and 1. So it all starts with 0 point whatever. Then you say, okay, well, whatever the one in the 10th slot is for this number, I'm going to take, so let's say that the number is 0.15. So I'm going to pick any of the 9 other options than 1 for that. So then we have we'll say 2. And then I'll go to the second element in the ordering that you've provided, and I'll take the 100th slot, so the 1 over 10 to the 2 slot for the second element, and say, okay, well, I'm going to pick any of the 9 other values that you didn't list. So let's say this is 0.16. So then, well, I can pick anything but 6 for this second decimal place, and then the same thing for the third decimal place, and so on and so forth. And so if you continue this process forever, then you would end up constructing this element that wasn't in any of the sets, because it differed from the first element in that first slot, it differed from the second element in the second slot, it differed from the third element in the third slot, and in fact it differed from every element that's already in this all-inclusive set in at least one slot. And so that is the irrationality of the irrational numbers, which are part of the real numbers. And it's that it always seems to be just a little bit wrong. No matter how you try to rationalize it, it's always at least a little bit wrong. And it follows from this argument. So even a failure to generate a one-to-one correspondence can be used in construction of a proof. And so the cardinality of the continuum, which is the size infinity that the real numbers are, is larger than the size of infinity that the countable numbers are. And so those are the first 2 degrees of infinity, and then you would construct additional infinities, I suppose, or orders of infinity, by considering dimensions of R and so forth. So these Cartesian products of these infinite sets and so forth. But whatever, that's all. This doesn't matter. It's irrelevant for now. Okay, so what else can we do? Well, in calculus, a fair amount of progress was made by considering limits, and so just passing to the limit, going to 0 in the case where you have something in the denominator that goes to 0, or whenever we're considering the derivative, you're taking these step sizes that get smaller and smaller, and you pass to the limit. They get infinitesimally small, but the ratio doesn't blow up, and in fact it settles into something. And so that turns out to be a really interesting result. And so this one, you have this limit as x goes to 0. Well, x is in the denominator, and this becomes 0. And sine of x as x goes to 0 goes to 0. So you end up with 0 over 0, which traditionally was nonsense. But by considering new methods, calculus was able to explain why this does not go off to 0, and it seems to settle to a very reasonable result of 1. This ratio is 1, and so there's a geometric proof of it, where that this tends to 1, and then there's you can use L'Hopital's rule and see that this goes to 1, derivative of the top over derivative of the bottom, and you can use the power series expansion for the definition of sine of x, and then that will also yield the result that this this ratio as x goes to 0 tends to 1. So this is known as a removable singularity. So normally 1 over x as x goes to 0 would take you to infinity, but the fact that it's a ratio of functions, you actually have something that kind of saves you from that, which is a pretty cool result. Okay. Limits or removable singularities can be one form of proof, and using limits to prove that. And then infinite series, which are another form of going to the limit. You're allowing this to go to infinity, and so you have this infinite series of approximations, which if you cut it off would yield some error, but you can drive the error down to 0 by going further and further, and so you can speak of passing to the limit, of letting your series go all the way to infinity and getting a reasonable result. One example for the usage of the exponential function is in computing compound interest, or continuously compound interest, where the interval of time between computation gets shorter and shorter and eventually disappears. Then at every instant you're actually getting interest on whatever your financial product is. That's another example. So we can go to 0, we can go to infinity, and in both ways, they're both speaking of infinity, but you have to put a little bit of thought into it, so it doesn't just, so you're not speaking garbage. But if you're clever about it, then you can use those as tools as well. All right, so jumping back to computer science, most of the problems that you'll run into as you're trying to prove stuff in discrete math and in computer science will be counting problems, and that's kind of what this course is supposed to be. I did take a broader approach to it, but in essence, that is what discrete math is. We're dealing with these discrete or integral values and trying to measure how a program's going to perform. Best, average, worst case scenarios of that program whenever the size of the input gets larger and larger. It goes from something small to something potentially very big. So how bad does it get, and how fast? That's kind of what I'm hoping to teach you by the end of this course. So if you're trying to prove that, if you're trying to prove something formally in terms of a program, the first thing that you have to do is believe that whatever it is that you're doing can be done. If you fail at this level, then it's not that there's no point in trying, it's that you've convinced yourself that there's no point in trying, which is very uninviting proposition. So you got to believe that whatever it is you're trying to do can actually be done, and that in a very real sense that is the first thing that you need to do. Then get moving a little bit. I always start with the definition. So if I have some proof that's asking me to prove something, right? So prove that the set of permutations acting on a collection of size n constitutes a group. Okay, well, the first time I saw that, I didn't know what it was asking. And so now, if I had to do this over again, the first thing I would do is write out the definition of a group. So, okay, it creates these parameters, these constraints on the problem. So, in order to prove that something is a group, I start with the definition of a group. You tell me what a group is, and then I'll tell you how this other thing that you've asked me about forms a group, right? So we start there, and then we define the set of permutations, and we define action, and then we say, okay, well, so an action takes, some set, and then it, does a thing to it, and it spits out a value. and then every time it spits out a value, it follows certain properties, these group properties. Well, okay, now that's something I can work with. So, starting with the definitions, while it feels like you're backtracking as you're going over it, that really is, the fundamental step. And you can start with the definitions. You can start with the field axioms, like we did whenever we were trying to prove that 1 was not equal to 0. And so, yeah, you just start with whatever you can, and then as you get further and further along, and you're trying to prove these things, then you'll be using definitions a little bit. You'll be using previously established theorems, and then I find it helpful. I always write them out. Like I rewrite them as many times as it takes. So that within the solution, as I'm trying to prove this thing, I can look up just a paragraph or two and see the formal definition of what I've already got established, or what I'm allowed to use essentially whenever making further assertions. And then it also puts the goalposts inside as well. Like you can see what it is that you have to prove in order to complete the statement or the assertion. And so, it's not glamorous. It doesn't feel like magic or anything. You're just stating the definitions. But honestly, that is more than nothing. That's a fair place to start, and that's where I always start. And then to get a little bit more momentum, you write some code. So, I mean, we hopefully, if you're in this class and you have at least some interest in programming, and so if you develop it and you decide to go into mathematics or to pursue it just a little bit further, that gives you an advantage over all of the other people, or mathematicians historically who have not had access to computers or programming or anything. It gives you a leg up. So it gives you this reasonable belief that perhaps progress can be made. And so I've already shown you a little bit with numerical integration in terms of how you can kind of leverage your understanding of programming a bit to get moving in the direction of a higher concept of mathematics, or a new way of looking at math. And so there was another problem that I was looking at. It was from complex analysis, and I was terrible at it, honestly. And so I just wanted to see if I could even understand what was being asked. And so I took what I knew. I found this package, this Python package called Sage, and it had defined the function that I was looking at. And then I just plotted it over and over again, and the method of getting a numerical result, it involved perhaps 100 or so computations for each one, or maybe just a few dozen. But in aggregate, within the first few days, I had asked my computer essentially to perform billions and billions of these computations. And it didn't really cost me anything. It cost me a couple hours in programming time, or maybe as much as like 10 hours or something, and then some processing time. So I had to wait a few minutes each time that I wanted to see something. But the equivalent of doing it by hand, with even a team of researchers or whatever, it would have taken centuries or longer. In order to to actually do this by hand, but because computers and programs are so fast, you can get results that would have been out of reach before, just by taking advantage of the discipline that you're instilling right now. So just keep that in mind, that it is something that you can take advantage of. This is something that will kind of prop you up as you go forward. So definitely take the time to build on your abilities and to grow them. It's an investment for any future problem solving that you're going to apply. So you have to keep your eyes out on how to apply it later on, but it's to your advantage very much to develop the discipline now. Okay, and then the last piece of advice is don't get stuck. Right, so if you're looking at something and it's new ground or something, it's just something that's completely unfamiliar to you and you don't really know what to do. Like I said, I start by going with the definitions, and then if that doesn't work, then I look over the theorems from before, and I just start skimming books and skimming proofs and glancing around and always moving. I avoid the scenario where I end up just sitting at my desk and staring at the wall, or trying to pull threads out of my shirt, whatever, this loose thread, trying to do that or whatever. If you allow yourself to get in that position, to get stuck, or to convince yourself that you're just bleeding clock until you can finally give up, well, then you've already done yourself in, right? So you got to keep moving. You got to find something. What is some form of work that, even if it doesn't feel like it necessarily solves anything, it at least moves me closer. It is productive labor. And so that's what you're looking for. And even if it's just doing the dishes, or something else, something that allows your mind to keep working, and you can see as some measurable amount of work, then that's progress. And you got to keep doing that, and you got to keep churning. And if you do that, you're at least giving yourself a chance. And that's pretty much where you got to start. Okay, so take a look at the review. Again, I'll post solutions sometime before the exam is due. Okay. Have a great weekend. Make sure you study. I'm sure you'll all do great. And after the exam, we'll start finding our way into proofs of this and that. Okay. See you later.